Hi everyone, and we have completed up till now we have completed 13 lectures. So we have successfully completed the first chapter, second chapter and third chapter, right? So the third chapter is coordinate systems. So we have completed that third chapter, coordinate systems, right? And also we have completed up till now 13 lectures, and this is lecture number 14, right? Okay. So here we are going to start a new chapter, that is fourth chapter, which is nothing but del operator or vector differential operator. So the del operator we can also call it as what? Vector differential operator, vector differential operator, right? Okay. Okay. So in generally this del operator or this vector differential operator so is represented by what here? It is represented as this del is equivalent to dou by dou x ax cap plus dou by dou y ay cap plus dou by dou z az cap. The units of this del operator are nothing but per meter or meter inverse, okay. So that is the units of this del operator. So the del operator mathematically we can represent it as dou by dou x ax cap, dou by dou y ay cap plus dou by dou z az cap, and its units are per meter, or we can write it as meter inverse, right? Okay. Okay. So now see here, see the del operator itself here, this del operator itself doesn't have any meaning until it operates on a function. See, it is just like if suppose if I write simply plus here, if I simply write plus, or if I simply write minus, or if I simply write into, or if I simply write divided by, okay. So these are nothing but what? These are nothing but operators, yes or no? So if I simply write the operators, does it have any meaning here? If I simply write plus, does it have any meaning? No. If I simply write minus, does it have any meaning? No. If I simply write into, or if I simply write divided by, there is no meaning for it. Understood? So the operator itself doesn't have any meaning until it operates on operands. Okay, suppose it is operating an operand, so let us say 4 plus 2, which is equal to what? 6. Now it is having some meaningful operation. So whenever this operator operates on operands, it is going to have some meaningful operation. So similarly, if I do here 4 minus 2, so then you are going to get 2 here. So here if I do 4 into 2, you are going to get 8 here, and here if I do 4 divided by 2, you are going to get 2 here. So the operator itself doesn't have any meaning until it operates on what? Until it operates on operands, right? Similarly, in the same manner, the del operator, so this is also what? This is also the vector differential operator. So it is also nothing but an operator. Okay. So that is a vector differential operator, yeah, vector differential operator, right? Okay. So this vector differential operator itself doesn't have any meaning. If I simply write the vector differential operator itself, it doesn't have, that means the vector, this operator itself doesn't have any meaning, right? Okay. So it is going to have some meaning whenever it operates on a function here, So this del operator is going to operate on two types of functions. One is scalar function and another one is vector function, right? Okay. So when the del operator, this del operator is going to operate, the del operator itself doesn't have any meaning until it operates on a function. So it is going to operate on two types of functions. One is a scalar function, let us say f of x comma y comma z, let us assume, and it can operate on a vector function. So vector function, let us say f bar of x comma y comma z. So this del operator is going to operate on scalar function, and also it is going to operate on a vector function. So what do you mean by scalar function and what do you mean by vector function? See, scalar function means, see actually what do you mean by a function here? Why we represent a function? See, the function is going to tell you how the physical quantity, how a physical quantity is distributed in nature. Understood? Suppose if I have given T of x comma y comma z, okay, let us say T represents the temperature. So the temperature distribution in three-dimensional space, if suppose if I have given as x square yz degrees centigrade, okay, so what this function is going to tell you? This is going to tell you how the temperature is distributed in three-dimensional space. So at 1 comma 1 point, the temperature is 1 degree centigrade. At 1 comma 2 comma 3, the temperature is 6 degrees centigrade, like that. Okay, so it is going to tell you how the temperature function or how the temperature is distributed in three-dimensional space. Understood? So a function will always tell you how a physical quantity is distributed in nature. Okay, that we can represent in terms of a function. Now here, since it is a temperature function, okay, so at each and every point here, at each and every point, this function is going to have only magnitude but not direction. So this type of function, we call it as what? We call it as scalar function. So for a scalar function, at each and every point, in space, that function is going to have only magnitude but not direction. So we know that the temperature is a scalar quantity. So at each and every point in space, this temperature function is going to have only magnitude. At 1 comma 1, we can say simply 1 degree centigrade. It doesn't have any direction. Okay, so that type of functions we call them as what here? Scalar function. Okay, so what do you mean by scalar function? Scalar function means at each and every point in space, that function is going to have only magnitude but not direction. That type of function we call it as scalar function, right? Okay, okay. So next, similarly, what do you mean by vector function? What do you mean by vector function? So vector function means at each and every point in space here, at each and every point in space, this function is going to have what? Both magnitude as well as direction. Understood? So that type of function we call it as vector function. See, for example, for vector function, I can represent in this manner. Let us say f bar of x comma y comma z. So this is a vector. This is a vector. So vector means it is going to have x component, y component and z component. Okay, so the x component, let us say the x component is a function of, in general it can be a function of x, y, z, right? So this is x component plus y component. So y component also in general a function of x, y, z. So this is y component, and z component. Z component is also in general a function of x, y, z. Right. So this is how you have to represent the vector function. So a vector function is going to have x component as well as y component as well as z component. So all these three components are functions of what? In general, they can be functions of x, y and z. Right. So for example, you can take here, let us say this is 2xyz ax cap plus x square yz ay cap plus xyz square az cap. So I can represent in this manner. So this is nothing but, for example, this is the example for a vector function. I can represent in this manner, right? Okay, so x component can be a function of xyz, y component can be a function of xyz, and z component can be a function of xyz. Understood? Okay, in general they can be x component, y component and z component. They can be functions of what? X, y and z. That is in general I am saying, right? So generally what the students will think is x component must be a function of only x, y component must be a function of only y, z component must be only a function of z. No, that is wrong. Right. So it is not mandatory that x component must be a function of only x, y component must be a function of only y, z component must be a function of only z. No. Right. Okay. So x component in general can be a function of x, y, z. Similarly, y component can also be a function of x, y, z, and similarly in general z component can also be a function of x, y, z. So this is one example. So now if you consider this vector function, if I take a point 1 comma 1 comma 1, so at that point what you are going to get? You are going to get 2ax cap plus ay cap plus what? Plus az cap. So that means this vector function at point 1 comma 1 comma 1, it is having what? It is having both magnitude as well as what? Direction. So at 1 comma 1 comma 1 we got this vector. So this vector is having both magnitude as well as what? Direction. Now if I change the point, I am going to get some different vector which is going to have both magnitude as well as direction. So which means the vector function is going to have both magnitude as well as direction. So at each and every point in space, this vector function is going to have both magnitude as well as direction, whereas scalar function is going to have only magnitude. Okay. So that is the difference between the scalar function and vector function. So I hope this point is crystal clear, right? Okay. So now whenever this del operator operates on a scalar function, it results in an operation called as a gradient. We call that operation as what here? Gradient. So in generally we will represent this with a gradient of f, right, where f is a scalar function, right? So gradient of f. So del is nothing but what? Del is nothing but vector operator, f is nothing but what? Scalar, right? So vector, you can remember like this. So this is vector operator and this is scalar. So vector multiplied by scalar results in what? Results in vector quantity, right? So the resultant of gradient is nothing but what? Is nothing but a vector quantity, right? Okay. Next, similarly, whenever del operates on a vector function, so it is going to result in two operations here. It is going to result in two operations. One is called as divergence. One is called as divergence operation, and another one is called as curl operation. So divergence operation we generally represent with del dot f bar. So here del is nothing but what? Del is nothing but vector differential operator, and f bar is nothing but a vector function, and you are doing the dot product between these two vectors. Yes or no? This is a vector operator and this is also a vector. Between these two you are doing the dot product. So the resultant of this one is nothing but what? Is nothing but a scalar quantity. The resultant of this one is nothing but a scalar quantity, right? Okay. So next is curl here. So curl means we'll represent this curl as what? Curl of f bar. We'll represent this as curl of f bar, right? Now here this del is nothing but the vector operator, okay. So del is nothing but the vector operator, and f bar is nothing but what? F bar is also a vector function. So now you are doing the cross product between these two. So the resultant is nothing but what? The resultant is nothing but a vector quantity, right? Okay. So the del operator itself doesn't have any meaning until it operates on a function, right? So it is going to operate on two types of functions. One is scalar function and another one is what? Vector function. So whenever it operates on a scalar function, the resultant operation we call it as gradient, and the resultant of gradient is nothing but a vector quantity. And whenever this del operator operates on a vector function, it results in two operations. One is called as divergence and another one is called as curl. The resultant of divergence is nothing but a scalar quantity, and the resultant of curl is nothing but what? Is nothing but a vector quantity. Understood? Okay. So these are the conclusions we have made. Right? Okay. So now we will see the physical interpretation of each and every operation. Right? So first we will see about gradient. First we will study about gradient. Okay, so once we complete gradient, then we will go for divergence. So once we complete divergence, then we will go for curl, right? Okay, okay. So next operation is gradient operation. So next we will start with a gradient operation. Right, gradient operation. So before this, I want to mention a note. See, this gradient, divergence and curl, all these three operations here, this gradient, divergence and curl, all are defined at a point. Understood? Okay, so make a note. So note is nothing but gradient, divergence and curl are defined at a point. They are defined at a point, right? Okay, so this is very important note here. This is very important note. Okay, one minute. Right. Okay, okay. So you have to keep this point always in mind. So that is gradient, divergence and curl. These operations are defined at a point. So this point you have to keep in mind, right? So now first we will see gradient. So first of all, we try to represent its mathematical representation. So what is its mathematical notation here? That is nothing but gradient of what? Gradient of f. So f is a scalar function. So whenever del operates on a scalar function, the operation is called as what? Gradient operation. So that gradient operation we can represent in this manner. So that is del multiplied by what? Simply a scalar function. So this is equivalent to what here? Del, we know that del is nothing but dou by dou x ax cap plus what? Plus dou by dou y ay cap plus what? Plus dou by dou z az cap. Okay, so this multiplied by what? This multiplied by some scalar function. In general, it is a function of x, y, z. Let us assume. Okay, okay. So now, if you multiply this, what you are going to get? You are going to get dou f by dou x ax cap. Every time I don't write a function of x, y, z like that. Okay, you have to understand that. So dou f by dou x. So that means take the total function and differentiate with respect to x. Right, then you are going to get the x component of gradient. Right, next multiply with this dou by dou y. Then what you are going to get? You are going to get dou f by dou y ay cap. Next, if you multiply, then what you are going to get? Dou f by dou z into what? Into az cap. So this is nothing but what? This is nothing but gradient of f. Gradient of f. Right. Now if you observe gradient of f, it is having x component and y component and z component. So which means the resultant is nothing but what? The resultant is nothing but a vector quantity. The resultant is nothing but a vector quantity. Right. Okay. So whenever you are doing this gradient operation, what you have to do is take the scalar function and differentiate that scalar function with respect to x, so that you are going to get x component. Next, take the scalar function and differentiate with respect to y, you are going to get y component. Similarly, take the scalar function and differentiate it with respect to z, you are going to get z component. So finally, this operation is nothing but what? Is nothing but the resultant is nothing but a vector quantity, since it is having x component, y component and z component. Okay, so the resultant of this is nothing but what? Is nothing but a vector quantity, right? So this is the mathematical notation or representation of gradient operation, right? Okay, so now we will see its physical interpretation, right? Okay, so first of all write down here, first of all write down the physical interpretation. So the physical interpretation of gradient, see, write down first, then I will explain. So gradient of a scalar function, gradient of a scalar function at a point results in a vector quantity. Gradient of a scalar function at a point results in a vector quantity which points in the direction of maximum increase in the scalar function, which points in the direction of maximum increase in the scalar function as you move, or I can say which points in the maximum increase in the scalar function from that point. Okay, or you can simply represent gradient of a scalar function at a point represents the steepest slope, or maximum slope of the function at that point. Okay, so so here gradient of a scalar function at a point results in a vector quantity, and that vector quantity is going to point in a direction in which the scalar function is increasing maximally from that point. Understood? Okay, so gradient of a scalar function at a point results in a vector quantity which points in the direction of maximum increase in the scalar function from that point. Or you can simply say gradient of a scalar function at a point results in a steepest slope or maximum slope of the function at that point. Okay, so I will explain this with some physical example here. So if we solve one or two problems based on this, then you can easily understand the meaning of gradient. Okay. See, whenever I am defining the gradient, what I am defining? Gradient of a scalar function at a point results in a vector quantity which points in the direction of maximum increase of the scalar function from that point. Okay, so gradient is defined at a point. So if you are having a scalar function and if you try to determine the gradient of that scalar function at a particular point, then it is going to result in a vector quantity, and that vector quantity is going to point in a direction in which the scalar function is going to increase maximally from that point. Understood? See, for example, I will give you one problem, then you can easily understand that, right? So write down this problem here, write down this problem. Okay, so write down this problem. Example, right? Okay. The temperature distribution in an auditorium, is given by T of x comma y comma z is equal to x square yz degrees centigrade. The temperature distribution in an auditorium is given by T of x comma y comma z is equal to x square yz degrees centigrade, right? Okay, okay. So now a mosquito located at a point 1 comma 1 comma 1, okay, a mosquito located at a point 1 comma 1 comma 1 desires to fly in a direction such that it has to get warmer as soon as possible. Okay, so the temperature distribution in an auditorium is given by T of x comma y comma z is equal to x square yz degrees centigrade. A mosquito located at a point 1 comma 1 comma 1 desires to fly in a direction such that it has to get warmer as soon as possible. Then determine its direction. Determine its direction. Okay, okay. So see here, what is the question they are asking? So they have given that there is an auditorium. So in that auditorium, the temperature is distributed as x square yz degrees centigrade. That means at 1 comma 1 comma 1 the temperature is 1 degree centigrade, and if you go to 1 comma 2 comma 3 location the temperature will become 6 degrees centigrade and so on. Okay, so this is how the temperature is distributed in an auditorium, right? Okay, so now a mosquito is located at a point 1 comma 1 comma 1. So in that auditorium a mosquito is located at a point 1 comma 1 comma 1. Now that mosquito desires to fly in a direction such that it has to get warmer as soon as possible. So if it has to fly in a direction, it has to fly in a direction in which it has to get warmer as soon as possible means it has to fly in a direction in which the temperature is increasing maximally from the point 1 comma 1 comma 1. So if it flies in a direction in which the temperature is increasing maximally from the point 1 comma 1 comma 1, then it is going to get warmer as soon as possible. Understood? Okay, so here they are asking what? They are asking in which direction it has to fly so that it is going to get warmer as soon as possible. Okay, so in an auditorium the temperature is distributed, and in that auditorium a mosquito is located at point 1, 1, 1. Now that mosquito decides to fly in a direction such that it has to get warmer as soon as possible. So if it has to get warmer as soon as possible, then it has to fly in a direction in which the temperature is increasing maximally from the point 1, 1, 1. So that means you have to determine what? You have to determine the gradient of temperature. If you determine the gradient of temperature at 1, 1, okay, so that is going to give you a vector. That is going to give you a vector which points in the direction of maximum increase of temperature from the point 1, 1. Right? Okay? Okay. So now first of all we have to determine gradient of temperature at 1, 1. So that is going to give you a vector which points in the direction of maximum increase in temperature at point 1, 1. Right? Okay. So first try to determine gradient of temperature. Right? Okay. Okay. So now here the given function is a temperature function, that is T of x, y, z is x square yz degrees centigrade. Right? Okay. So gradient of T, you have to determine gradient of T. So gradient of T is equivalent to what? Is equivalent to dou T by dou x Ax cap plus what? Plus dou T by dou y Ay cap plus dou T by dou z Az cap. See, every time there is no need to expand the gradient in this manner. So we know that whenever we are doing gradient, okay, we have to take the total function and differentiate with respect to x in order to get the x component, and take the total function and differentiate with respect to y to get the y component. Take the total function and differentiate with respect to z to get the z component. So directly you can take this one, differentiate with respect to x to get x component, differentiate with respect to y to get y component, differentiate with respect to z to get z component. Okay, so there is no need to write this expansion every time, right? Okay, so for the first time I am writing each and everything. So if you differentiate this temperature with respect to x, what you are going to get? You are going to get 2xyz Ax cap, and differentiate this with respect to y, you are going to get x square z Ay cap, and differentiate this with respect to z, you are going to get x square y Az cap. So this is gradient of T. This is gradient of T. So we want a gradient of T at point what? At point 1, 1. So at 1, 1, what you are going to get? 2Ax cap plus what? Plus Ay cap plus what? Plus Az cap. Okay, so is the problem completed here? Is the problem completed? No. Why? Here we have determined the vector. You have determined the vector, okay, that is going to point in the direction of maximum increase in temperature from point 1, 1. But here what they are asking here? They are asking the direction, then determine its direction. So they are asking only direction here. So I have already told in the first class itself, whenever in the problem they have asked direction means you have to determine what? You have to determine the unit vector. Okay, so generally a vector is going to have both magnitude as well as what? Direction, and the direction is always given by what? Given by the unit vector. Okay, so here what we have determined? We have determined the vector, right? So at point 1, 1. Right, so they are not asking us the vector, they are asking us only direction. So direction means you have to determine the unit vector. So how to determine the unit vector here? So the unit vector along gradient of T at point 1, 1 is equivalent to what? Is equivalent to gradient of T at 1, 1 divided by magnitude of gradient of T at 1, 1. So take the vector and divided by its magnitude, that is going to give you the unit vector. And this unit vector will always gives you what? Will always gives you the direction. Always gives you the direction. Okay, so if you do this, what you are going to get? Tell me. So you are going to get 2Ax cap plus what? Plus ay cap plus az cap divided by what? Divided by square root of 2 square plus 1 square plus 1 square. So which is equal to 2ax cap plus ay cap plus az cap divided by what? Divided by square root of 6. Right? Okay. So this is the direction. This is the direction in which the mosquito has to fly from the point 1, 1, 1 in order to get warmer as soon as possible. Right? Okay. Okay. So from this example, I hope you have understood clearly what do you mean by gradient. Right? Okay. Okay. See, in the previous problem, so if I change the point here, so instead of giving the point at 1, 1, if I give the point as 1, 2, 3, then gradient of t is going to change, right? Then the direction in which the mosquito has to fly is going to change, right? So the gradient is defined at a point here. If you change the point, the gradient is also going to change. So remember that, right? So that is very, very important. Okay. So here a mosquito is located, this is mosquito, right? Okay. It is located at point 1, 1, 1. Now it decides to fly in a direction in which it has to get warmer as soon as possible. That means it has to fly in a direction in which the temperature is increasing maximally. So that means from here it has to fly in a direction such that this direction is given by what? This direction is given by 2ax cap plus ay cap plus what? Plus az cap divided by what? Divided by root 6. So from this point, if it flies in this direction, then it is going to get warmer as soon as possible. See, from this point it is having many ways to fly. Yes or no? It can fly in this direction, it can fly in this direction, it can fly in this direction, it can fly in this direction. There are infinite number of ways to fly. Okay, but I want it to fly in a direction such that it has to get warmer as soon as possible. That means it has to fly in a direction in which the temperature is increasing maximally. So that means you have to find out the unit vector of gradient at point 1, 1, 1. Right? Okay. So that's what we have done. Okay. So I hope this problem is crystal clear, and I hope you have understood the meaning of what? The meaning of gradient, right? Okay. Okay. So generally the gradient of f, the magnitude of gradient of f can also be represented with dou f by dou L maximum, right? Okay. So I have told gradient of f will represent what? Will represent the maximum slope or steepest slope at a point. So that's why in general the magnitude of gradient of f in generally we can represent, this is just a notation here. Okay, just we can represent it as a dou f by dou L maximum, just for understanding purpose, right? Okay. Okay. So magnitude of gradient of f is nothing but the maximum slope of the function at a point. So gradient of f is going to give you the maximum slope or steepest slope of a function at a point. Okay. Okay. So now see here. Now write down another problem. So write down another problem on gradient. So the height of a certain hill, is given by h of x comma y is equal to 10 into 2xy minus 3x square minus 4y square minus 18x plus 28y plus 12. Okay. So the height of a certain hill is given by, see how the height of the hill is varying, that is given by this function, right? Okay. Okay. So now question number A, they are asking where is the top of hill located? Where is the top of hill? Where is the top of hill located? So this is the first question they are asking, right? Next, B. How high is the hill? How high is the hill? This is second question. Next, third question. Determine the direction of steepest slope. Determine the direction of steepest slope at point 1, 1. At point 1, 1. Okay. So these are the questions they have given, right? So what they have given here? They have given the height of a certain hill is given by. So how the height of the hill is changing? How the height of the hill is changing? So that is given by this function here, this function, right? Okay. So this function, that is 10 into 2xy minus 3x square minus 4y square minus 18x plus 28y plus 12. So this is how the height of the hill is changing, right? Now they are asking, question number A, they are asking where is the top of hill located? Question number B, they are asking how high is the hill? And C, they are asking determine the direction of steepest slope of this function at point 1, 1, right? Okay. Okay. So the first one, what they are asking, where is the top of hill located? Where is the top of hill located? So how to determine where is the top of hill located? Tell me. See, if you consider a hill here, if you consider a hill something like this, okay, it is varying like this, right? So let us say this will become what? This will become the top of the hill. So at the top of hill here, what is the slope you are going to get? At the top of hill, the slope at this point, right? At this point is nothing but the top of hill. So at this point, what is the slope here? Slope is equal to what? Slope is equal to 0. Slope is equal to 0. Understood? Okay. So the slope of the function must be equal to 0 at this point. So which means the gradient of h must be equal to what? Gradient represents what? Gradient represents the maximum slope or steepest slope of the function at a point. Understood? So at this point, the maximum slope or steepest slope, or you can simply call it as slope, whatever it may be, so it will be what? It will be equal to what? It will be equal to 0. So at the top of the hill here, at the top of the hill, if you move in this direction or in this direction or in this direction or in this direction, whatever may be the direction you will move, right, the slope will be what? The slope will be 0. Understood? So here, once you reach this point, after this, the height of the hill is not at all increasing. Whatever the direction you will move from this point, the height of the hill is not at all increasing. Understood? So which means the gradient of h at that point will be equal to what? Must be equal to 0. Right? Okay. So try to determine the gradient of h is equal to 0. So from that, try to determine the location of what? The location of top of hill. So that means they are asking to determine this point here, to determine this point. So let us say this point is x comma y. So you have to determine this x comma y values, right? Okay. So gradient of h is equal to 0 at the top of hill. So now see here. Now what is h here? H they have given as h of x comma y is equal to 10 into what? 10 into, so I am just copying this one here, this function. So I will copy this function. Okay. So I am copying here, right? Okay. So you have to make gradient of h is equal to what? Is equal to 0, right? Okay. So determine gradient of h here, determine gradient of h. So what I have told here, what I have told, whenever you are determining gradient, what you have to do, take the total scalar function and differentiate it with respect to x in order to get x component, and differentiate it with respect to y in order to get y component, and differentiate it with respect to z in order to get z component. And if you observe here, there is no z here. Understood? So if you differentiate this function with respect to z, you are going to get 0, right? So you can just differentiate this function with respect to x and with respect to y. So if you differentiate this with respect to x, what you are going to get, tell me? So 10 into, differentiate this total function with respect to x here. So what you are going to get? You are going to get 2y. You are going to get 2y minus what? Minus 6x minus what? Minus 18. That's it now. If you differentiate with respect to x, this is what you are going to get. So 2y minus 6x, right, minus 18. So this is x component plus 10 into, right. What is the y component here? In order to get the y component, take this total function and differentiate with respect to y. So if you differentiate this with respect to y, you are going to get what? 2x minus 8y plus what? Plus 28, right. So this is nothing but y component. So this is gradient of h. So this must be equal to what? This must be equal to 0, right. If you differentiate with respect to y, 2x minus 8y plus 28, right, ay cap must be equal to 0. So for this gradient of h to be equal to 0, so this component must be 0, and also this component must also be what? Must also be 0. So then only this gradient of h will become equal to 0. Understood? Okay. So here you are having 2y minus 6x minus 18. So this must be equal to 0, and here you are having a plus 2x, here I am writing minus 8y, right, plus 28. This must be equal to what? This must be equal to 0. Okay. So solve this one here, solve this one. What you are going to get? So here you can multiply this with 4 here. If you multiply this with 4, what you are going to get? You are going to get 8y minus 24x minus 72, or equivalent to 72. I can write in this manner. Yes or no? Next, so here you are having minus 8y plus what? Plus 2x is equal to what? Is equal to minus 28, right? Okay. So in this manner I can write. Now here if you add these two, so 8y minus 8y will get cancelled. So minus 24x plus 2x, that is minus 22x, minus 22x. So this is equivalent to, right. Eight y 24 72, right. Okay. So you are getting minus 22x is equal to 72 minus 28. So what is 72 minus 28 here? So 72 minus 28, so is 44. So that is 44, right. So 44 divided by 22 is 2. So therefore x is equal to what? X is equal to, we got minus 2. X is equal to, we got minus 2, isn't it, right? Okay. Okay. So x is equal to minus 2. Correct na? So check the calculations here. Right. Right. Okay. So x is equal to minus 2. Now now substitute x is equal to minus 2 in this equation here. What you are going to get? Minus 8y, right, in this equation substitute. So minus 8y plus 2 into what? Plus 2 into minus 2 plus what? Plus 28 is equal to 0. So minus 8y is equal to what? So here you are going to get minus 4, and here this is 28. So 28 minus 4, 28 minus 4 is 24, right? So if you take 24 to this side, you are going to get minus 24, minus minus will get cancelled, 8 1s are 8 3s are. So therefore y value is equal to what? Y value is equal to 3. So x comma y, therefore x comma y is equal to what? Is equal to minus 2 comma 3. Okay, so this is the point where the top of the hill is located. Understood? Okay, so for question number A, where is the top of hill located? So the top of the hill is located at x comma y is equal to what? Minus 2 comma 3. So this is the point at which the top of the hill is located. Next, what they are asking here? B, they are asking how high is the hill. Okay, so if you want to determine how high is the hill, what you have to do? Just substitute this. Yes or no? So at this point the top of the hill is located. Understood? If you just substitute this x and y values in this expression, then you are going to get the height of the hill. So this is the point at which which gives the top of the hill location. So if you substitute this point in this expression, you are going to get what? You are going to get the height of the hill. Understood? Okay, so just substitute here what you are going to get. So h of x comma y, so substitute here, substitute in place of h of x comma y is equal to what? 10 into what you are having here, what you are having, or otherwise I will copy this, function once again, right? Okay, so we can do it, copy this one here, copy this one, right? Okay, so for B question here, for question number B, right? So substitute h of minus 2 comma 3. So what you are going to get? 10 into 2 into minus 2 into 3 minus 3 into minus 2 whole square minus 4 into 3 whole square minus 18 into minus 2 plus 28 into 3 plus 12, right? Okay, so what you are going to get? So here 2 3s are 6, 6 2s are 12, so minus 12 you will get, and here so 3 4s are 12, 3 4s are 12, right now 2 2 4, 4 3s are minus 12, and here 3 4s are 12, here also minus 12, and here 9 4 36, so here you will get minus 36, and here minus into minus plus, so here you will get plus 36, and here 28 into 3, 84, and this is 12, right? Okay, so here minus 36 plus 36 will get cancelled, so minus 12 will become minus 24, right? 84 plus 12, 96, right? So 96 minus 24 is 72. So 72 into 10 is 720. So we got height of the hill as 720 meters here, 720 meters. Okay, so height of the hill, height of hill is equal to what? Is equal to 720 meters, right? Next what they have asked here? What is the direction of the steepest slope at point 1 comma 1? At point 1 comma 1. So which means you have to determine what? You have to determine the unit vector of gradient of h at point 1 comma 1. So they are asking the direction. C, question number C, what they are asking? They are asking the direction of the steepest slope. Steepest slope means what here? Steepest slope means gradient. Understood? Okay, so they are asking the direction, that means you have to find out the unit vector along gradient of h. So if you try to determine the unit vector along gradient of h at point 1 comma 1, what you are going to get? You are going to get gradient of h at 1 comma 1 divided by what? Magnitude of gradient of h at 1 comma 1. So I hope you can do this here. I hope you can do this, right? Okay. Okay. So what is gradient of H? Already we have determined here gradient of H, right? Okay. So what we got? We got this. This is nothing but a gradient of H. We have already determined this one, right? Okay. So this is gradient of H, right? Okay. So now gradient of H at what? At 1 comma 1. So just substitute here 1, right? And substitute here 1, and substitute here 1, substitute here 1, right? Okay. Okay. So then what you are going to get? You are going to get here 2, 6 into 1 is 6. Okay. Here 2 into 1 is 2, 8 into 1 is 8, right? So this is what you are going to get. So 2 minus 6, 2 minus 6 is minus 4, minus 4 minus 18, so that is minus 22. So this is minus 22. And here 2 minus 8 minus 6, minus 6 plus 28, minus 6 plus 28, that is 22. Okay. So here you are going to get, minus 220 here, minus 220 Ax cap, and here you are going to get plus 220 Ay cap, right? Okay. Okay. So therefore I am writing this here, the direction I am writing here. Okay. Okay. So what we got? Gradient of H at 1 comma 1, what we got? We got minus 220 Ax cap plus what? Plus 220 Ay cap divided by what? Divided by square root of 220 whole square plus 220 whole square. So that is I can write 220 root 2, right? So here 220 will get cancelled. You are going to get minus Ax cap plus Ay cap divided by what? Divided by root 2. So this is the direction of the steepest slope at point what? At point 1 comma 1, right? Okay. Okay. So I hope this is crystal clear. So this is the direction. So problem number C is also completed. Okay. So I hope you have understood what do you mean by this gradient with the help of these examples, right? Okay. Okay. So this is enough here. This is enough. So just you have to understand that the gradient is defined at what? Defined at a point, and whenever you try to determine the gradient of a scalar function at that point, it is going to result in a vector quantity, and that vector is going to point in a direction in which the function is increasing maximally. Understood? Okay. So if you understand these things, then that is more than enough, right? So with this we have completed the topic of gradient. So in the next lecture we study about flux and divergence, right? Okay. So I hope you have enjoyed this lecture. So with this I am winding up this session. So this is the end here. This is the end of this lecture. This is the end of this lecture. Okay. So I hope you have enjoyed this lecture. So we will meet in the next lecture. So until then, take care. Bye bye.